Hello, Mr. Myers here, bringing to you a recap of this week on valence electrons, Lewis dot diagrams, and finally ionic bonding. So first, let's review the valence electron idea. We started off on Monday taking a look, say, at hydrogen, and we said that hydrogen, as I zoom in a little bit more, has one electron total. And so we demonstrated that by showing a nucleus and a ring around the nucleus. And this ring represents the number of energy levels present for hydrogen, which hydrogen, as we see in the periodic table, is in the first row. That first period means that it has one energy level. And so what we do is we place the one electron in that energy level, kind of like this. And then we followed that up with talking about valence electrons. And we said valence electrons are electrons in the outermost energy level or in the outermost shell. And so we look at hydrogen and say, well, it's got one shell and there's one electron there. So this has one valence electron. Okay. We follow that up also then in saying that hydrogen, for a Lewis dot structure, we take the element symbol and place the number of valence electrons around it as a symbol, kind of like this. Okay. We did a second example where we looked then at lithium. And you guys said that lithium had 3 electrons total and that it was in the second period. So this means that lithium has 2 energy levels associated with it. The first one, and then a second one. So if you look at your periodic table, you'll notice that the first period has 2 elements in it total, and that represents that there can only be at most 2 electrons in that first level. So you've got one here, another there. Now, lithium has 3 electrons total, so we've got one more to go. And we put it out there in the second level. And so now we say, well, how many valence electrons are present? We say there's 1 electron in this outermost energy shell or energy level. So lithium has 1 valence electron. And we show that as lithium with a dot for the electron. Okay, we did another example then of aluminum. You guys said there were 13 electrons total and that it was in the third period. So this means aluminum has 3 energy levels associated with it. 1, 2, and 3. Again, that first level can only have 2 electrons. The second level we'll find can only have 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons in that second level. Total there are 10. We need 13, so we're going to put 3 more in that outermost energy level. And what we see here is there are 3 in the outermost shell, so there are 3 valence electrons present. And we demonstrate that with the Lewis dot structure having 3 dots around it. Now the trick we said in class after we went through all this process is to say that the group number tells us the number of valence electrons. So recall that hydrogen is in group 1, so it has 1 valence electron. Lithium is also in group 1, so it has 1 valence electron. And aluminum is in group 3, so it has 3 valence electrons. So then you went through all that process, and we did the Lewis dot side of the sheet at the end of class on Monday. You should have seen for calcium that there were 2 dots like that. I'll write a little bit bigger. Potassium would have 1. Argon has 8. It's in group 8, so 2 per side. Aluminum we just did with 3. Bromine is in group 7, so it should have 7 valence electrons, one that's lonely there. Carbon is in group 4, so it has 4 valence electrons. Helium is in group 8 as a noble gas. However, the atomic number is 2, so at most it has 2 electrons. And you'll notice I paired them together like this because it is noble gas, and this demonstrates that it's stable and that it won't bond to anything because it doesn't have any lonely electrons wanting to bond. You also had oxygen, group 6, so 6 valence electrons. Phosphorus, group 5, has 5 valence electrons. And then hydrogen we saw above is in group 1 with 1 valence electron. At this point, turn over to the next side that says ionic bonding. All right. So looking at this side, I said not to do it on your own because, as it would turn out, these components are incorrect, and I wanted to show you how to go about this correctly. So in the first example, you have sodium with chlorine. And Lewis dot structures play an important role here. Remember, with ionic bonding, we're going to show that a metal reacts with a nonmetal. Okay, or it doesn't react, but that they bond together. They have a transfer of electrons. Specifically, the metal is going to give its electrons to the nonmetal. So the metal loses the electron and becomes positive. We call that a cation. And then the nonmetal is gaining electrons. It becomes negatively charged, and we call that an anion. And the number of electrons transferred or accepted will give us some idea about the value of the charge. Okay, so let's look, I'll draw this again below, sodium and chlorine. Sodium is in group 1, so it has 1 valence electron. Chlorine is in group 7, it has 7 valence electrons. And we want to put these two together. Sodium is a metal, it's going to lose the electron. Chlorine is the nonmetal, it wants to gain it. So I draw an arrow like this to show that the electron from sodium is transferring over to chlorine. And the result is that we get a sodium ion where it's positive because it loses the electron. And then chlorine has gained an 8th electron, so it becomes negatively charged. And we put chlorine in brackets to house all the electrons to be on the safe side and to recognize that, hey, we've gained an electron, it has the octet, but we don't know specifically where that electron is around the atom. So this part is different from your sheet that you had right here. Okay, so do it my way as I'm doing it on the line paper. So this whole thing we need. Now another example that's on your page is you take calcium, which has 2 valence electrons, and then you have 2 chlorine atoms, each with 7 valence electrons. Hopefully what we see is that the calcium has 2 electrons to give, each chlorine can accept 1 each. So 1 electron will go to the top chlorine, the other one will go to the bottom chlorine. And the result that we're getting is we have a chlorine anion with 8 valence electrons around it, the octet. Remember the octet, we want to be getting this idea that we're isoelectronic. They're isoelectronic with the noble gases. That's the idea of stability here. So we've got the chlorine, then we have a calcium ion. It's a +2 because it loses both electrons. And then we have our other chlorine anion. We call it chloride. Okay. Do not do it the way it's shown on the paper where they don't show the electrons at all, but rather this method is what I expect you to do for it to be correct. Okay. Now, there were some questions asked on Tuesday about, what if you change the element so it has, the metal so it has a different number of electrons, or they don't necessarily match up with the non-metal. So I have another example. Let's say you're told, take potassium with nitrogen. First, we need to identify the number of valence electrons for each. Potassium is in group 1, so it has 1 valence electron. Nitrogen is in group 5, so it has 5 valence electrons. Notice here that potassium can give 1 electron, while nitrogen wants to gain, so give or lose up here, nitrogen wants to gain 3 electrons. So I'll rewrite it to the side. And we can say, hey, potassium's going to give its electron to nitrogen, which is great, but now nitrogen still has 2 electrons that are lonely and want to bond. So what we'll do is we can add another potassium. It's a source of the electron. It can donate the electron to nitrogen. And then we see we need yet another potassium atom that's a source of another electron to give to nitrogen. The result here is a couple of, actually a few, it'd be 3 potassium ions and a nitrogen anion. We call this one nitride. So notice the nitrogen wanted to gain 3 electrons, informing us that we should expect it to have a -3 charge as an anion. And to be stable and neutral, all charges, I'll put it down here, all charges must balance. In other words, they must add up to 0. Okay, so if we have a -3 here, we need to expect a +3 or 3 positives to come from potassium. Since each potassium is a +1 charge, we need 3 of them in order to make this scenario work. Go ahead and give the other 5 problems on your sheet a go. The way it's shown is like number 1, it's KF, so you're looking at the formation of KF. And number 2, this is actually 2 iodine with the magnesium, so we should have 1 Mg, 2 iodine in the formula, so on and so forth throughout the rest. Good luck.